This presentation is delivered by the Stanford Center for Professional Development.
Okay, well, today we'll finish up Newton's method. Might take much of the day, though. But then we'll move on to our absolute last topic, which is interior point methods for inequality constraint problems. So we're studying methods, Newton's method, for solving the following problem. You want to minimize f of x, which is smooth, subject to ax equals b. So we're assuming here that ax equals b is feasible. I mean, otherwise the problem is the whole problem is infeasible, and that we have a starting point x0 that satisfies ax0 equals b. So we assume we have a feasible point, and we're actually going to, the first method we're going to look at, which is the basic Newton's method, is a feasible method. That means that every iterate will be feasible. They'll all satisfy ax equals b. The reason for that is simple. The Newton step at a point x is the solution. It's actually this is the Newton step. It's found by solving this set of equations here. And that's the Newton step. We looked at what it means last time. Now the second block equation says a delta x Newton equals 0. So it basically says that this search direction is in the null space of A. Now, what that means is very simple. It says that if you have a point that satisfies ax equals b, and you add any multiple, that's the step length, times an element in the null space of A, obviously you continue to satisfy ax equals b. So feasibility is guaranteed. All iterates are going to be feasible no matter what the step lengths and so on. This is the basic Newton method. Okay. So Newton's method looks like this with equality constraints. I guess you'll be implementing one. Some of you may already have. In fact, we know some of you already have because you've written with questions. So, but all of you will be shortly writing up a Newton's method with equality constraints. So it works like this. You're given a point in the domain of f, of course, with ax equals b. And you compute this Newton step. That's by solving this set of equations. This set of equations has got lots of names. It's I guess mostly this is called the KKT system, is what this is, because it's not the KKT system, this thing. I guess this is called a linearized KKT system. That's called a KKT matrix because that's where it comes up. A lot of people would just call this the Newton system. So you compute the Newton step. If the Newton decrement is small, you quit. Otherwise, you do a line search you just do a standard backtracking line search. So you try t equals 1. If that gives you enough decrease, fine. Otherwise, you choose beta times t, beta squared, and so on. Beta squared times 1, otherwise known as beta squared. And then you finally update. Now, this method has the following attributes. The first is, of course, it's always, the point x is always feasible because every step, every direction, all of these things are in the null space of A. And if the original A satisfies ax equals b, that's preserved because of this. So it's a feasible method. And of course, it's a descent method. So f goes down at each step. And that's ensured by the line search. Okay. Now this method is affine invariant. That's easy to show. If you change coordinates, you generate exactly the same iterate. So you get a commutative diagram there. It has all the features you'd expect to see of Newton's method, which is this affine invariance. What's interesting about it is, in fact, this is identical to applying unconstrained Newton's method to after you use elimination of variables, linear elimination of variables. So it's absolutely identical. That means it means we don't have to have a new convergence theory or anything like that. You don't have to see a new proof because you've already seen it. It also means that all the practical stuff you've seen about Newton's method, which is like the fast convergence, the quadratic, all that sort of stuff, that's absolutely preserved here. Okay. So you might ask, if it's the same, why do you have to go through all the trouble of formulating it this way and not by elimination of variables? And actually, it's a good question. I'll answer it right now. The reason is this. There's no reason. There's a lot of people who would think that eliminating variables is better. And there are actually cases where it is better. I'll tell you right now when and why it is not. If this matrix here has structure and then you eliminate variables, eliminating variables can destroy the structure. So actually, if there's one thing you should take, you should take away, like, I don't know, we'll make a little trifold card. That's too much even. We'll make a little wallet card of the things you should remember when you leave this class. But one of them should be, it is not always better to solve a smaller set of equations. In fact, in many, many cases, it's far better to solve a much larger set of equations, provided A, those equations are structured, and B, you intelligently exploit the structure. Okay, so, I mean, these are kind of obvious, but you'd be shocked how many people don't know these things. Or know them, but kind of don't apply them to their everyday life or something like that. Okay, so, all right. This is Newton's method. And you'll be implementing one, it works, and so on and so forth, has all the attributes you've seen. Self-concordance, it's all identical. Then you get an absolute complexity bound on the number of steps required and so on. There's a variation on Newton's method that's very interesting. It won't play a big role for us, but it's actually important to point out. So here it is. There's a variation on Newton's method called an infeasible Newton method. And in an infeasible Newton method, it's actually very, very interesting how it works. You want to minimize f of x subject to ax equals b, something like that. In the feasible Newton method, the original x is feasible, and then every iterate after that is feasible. So you will always satisfy ax equals b. There's another version of this which works like this. You're actually allowed, for intermediate steps, to actually not be feasible. So I can start with any x I like. So here's an example. You're solving this one, or you will solve shortly on your homework this. You'll minimize minus some log xi. I think. I can't remember. Is this what you're solving? I think it is, yeah. Something like that, subject to x equals b. Okay? So actually, finding a, I think this is what you're solving, right? Yeah, it is. So here, in an infeasible method, you're allowed the following. By the way, in an infeasible method, you cannot be outside the domain of f. So you must have x positive. Actually, that's true of a feasible method as well, obviously. You must have x positive at each step. However, you are absolutely allowed to have ax equals b violated. So in other words, you could start with x0, that's just like 1. Okay? Just then you're nicely in the domain here. But for example, unless you're very lucky, you don't satisfy ax equals b. Now, if you have a method like that, there's a couple things that get trickier. The convergence gets a little bit trickier, not much. But the first thing is you cannot have a descent method. In other words, in this problem, you cannot expect the objective to go down. Because the objective actually is meaningless until you're feasible. So some kind of combination, what should go down is going to be some combination of the objective or some measure of suboptimality and the residual. By the way, once x is feasible, then it makes sense to talk about the objective. But until then, it hardly matters. And indeed, it's clearly not a feasible, a descent method, because if you start with an x for which f is very small, smaller than the optimal value, it's going to have to increase as iterations go. Okay? So watching this algorithm, you're going to want to look at two things. You're going to want to look at things like ax minus b, that's the so-called primal residual. And the other thing you'll look at is the dual residual, which will give you the optimality conditions. So here, the way it works is this. In this case, it's no different. You simply linearize the optimality conditions, and you get a set of equations that look like this. By the way, it's identical. If you're feasible, this is identical to the Newton direction for a feasible point, because in that case, the primal residual is 0. Okay? So whatever this is, this Newton step at infeasible point, it is a generalization of the Newton step when you're feasible. Okay? However, it allows a non-zero point here. And this, so you can actually, let's see, we can actually work out a couple of interesting things. We can see the following. If it is always the case that x plus delta x Newton is feasible, and you can see that directly by this bottom row. This bottom row says a delta x equals minus ax minus b. So in other words, if you multiply it, if I multiply it by this, I get ax plus a delta x Newton. And from this bottom equation here, a delta x Newton is minus ax plus b. And I'm done. Okay? So ax is b. So if you take a full Newton step, you will be feasible. Okay? By the way, in this method, if you ever take a full Newton step, the following iterate will be feasible. Once it's feasible, the Newton step you're calculating by the infeasible start is identical to the Newton step for the feasible Newton method. Okay? So, all right. That's actually a good thing to know. I'll say a bunch more about that. So in other words, what happens is, we haven't even gotten to the infeasible start Newton method, but what will happen is if you ever take a step of size 1, a full undamped step, people call that, then the next iterate will be feasible, and all future iterates after that will be feasible. So you'll achieve feasibility. Okay. And let's see what, and people, you can interpret it this many ways. You could say simply that you're linearizing the nonlinear optimality conditions. You can also, maybe that's the best one. That's maybe the simplest way to do it. Right. Some people would also call this a primal dual Newton method because you're updating both the primal variable and this dual variable at the same time. Of course, that's true of Newton's method as well, but still, I guess that's the idea. So this is infeasible start Newton method. Looks like this. You start with a point. It has to be in the domain of the function, but it does not have to satisfy ax equals b. So does not. And you start with some initial Lagrange multiplier. Actually, it turns out the initial Lagrange multiplier is totally irrelevant, but that's doesn't matter. You compute the primal and dual Newton steps. You compute these. Then here's the important part. You cannot do a line search on the function value. Makes absolutely no sense. And in fact, in the infeasible start Newton method, the objective can and will, and in fact, indeed, in some cases, it must increase. So it can't go. And the reason is very simple. Well, here, I just give you let's just do a really simple example. Here's your equality constraint. Gives you that's the feasible set. And here are the sublevel sets of your objective. So here, I'll just draw the optimal point. There's the optimal point. Okay? What if you start right there? Well, f is now at its unconstrained minimum. That's the optimal point. So f has to go up, going from here to here. So obviously, a descent method is not going to do the trick. I mean, at all. Right. By the way, in a problem like this, if the function were quadratic, what would the Newton step be here? The infeasible start Newton step, what would it be from here? What would it be? 1. It would be, the step you'd take would be 1, but the Newton step, which is actually the increment, would point exactly to the optimal point. Because what you're doing is you're making a quadratic approximation. The function's quadratic, it's not an approximation. Then you're solving the quadratic problem by the linear equations, and you will get this. You will take a step of 1, and you'll converge to the global solution in 1 step. If it's non-quadratic, it might not point there. It might point, over here. By the way, the infeasible start Newton method will always point to a point on this line, because if you make a single step of size 1, you are feasible, and therefore you're on this line. So it might even point, I don't know. It seems unlikely, but it could point over here. I could make some sick function that would do that. It would point over here. But if you made a full step, you are then feasible, and all subsequent steps will be on this line, will stay in this line. If you make a half step, you might be here, and so on. So that's the picture. You must, the line search is actually done on the norm of the residual. And let me tell you what that is. The residual is R dual and R primal. It's like this. It's this norm. Okay? So this is, I guess people call it a merit function or the Lyapunov function for this process. That's a function which proves convergence of something by, in this case, it proves that RD and RP goes to 0. It certifies RP and RD going to 0 because it's a function that is non-negative, positive only, 0 only if you're 0, and goes down at each step. So this is what goes down. It's not very different. And then R primal and R dual, that's just these. No, I'm missing. This is not quite it. Sorry. This you have to add plus. There it is. Sorry. There it's right there. That's. This is R dual, and that's R primal. Okay. So when you run one of these, you want to look at R primal and R dual. Here's what you want to see. you want to see R prime will go to 0 and stay 0. Actually, if it goes to 0 and then later becomes non-zero, you have a bug. And then R dual will then very rapidly go to 0. Okay? In fact, quadratically in the end game. So you have the norm. By the way, it's the norm. It is not the norm squared here. So just to make a point here. Obviously, both of those go down. But if you work out the following, if you work out the d dt of the norm of the residual as a function of the step length at t equals 0 and in the Newton direction, you will actually get, I believe, it's minus 1 or something like that. Or it's actually minus the residual. There you go. It's that. I haven't. This is worked out in the book, but you can work this out. It's this thing. What this says is that if you take a step of alpha, if you take a step of t, the predicted decrease is simply this. It just scales the residual down. That's your predicted decrease. You have to degrade that because this is a lower bound by convexity. It's a lower bound. And you scale it back, and alpha can be any of the constants you like, 0.1, 0.01. It appears to not have make any difference what value of alpha you use over a huge range. So this is what goes down. It's a residual. That's your line search. By the way, it's sometimes when you get feasible, you can switch your line search back to F because now it coincides precisely with the original Newton method and so on. Okay. This is what I was trying to. I was trying to recover this here. So that was the. This is the descent condition. That's the directional derivative of this at t equals 0 plus is this thing. Okay. Actually, you don't have to worry about all these things. This is just sort of to get a rough idea of how the method works. This is actually a very, very good method choice in some cases. If you have a point that's like not quite feasible or something like that, but it's easy, for example, if you're doing a so-called warm start. Warm start means you just solved a problem just like the last one, except now it changes a little bit. So doesn't really matter what you're doing, but you just solved a problem just like the last one. The data changes a little bit. One more piece of information comes up and comes in an estimation problem, something like that. One more data point becomes available. One more time step has evolved, or something like that. Then what you do is you can use this with warm start. And in fact, if you're lucky, it would be something like just 2 Newton steps, or 1 would get you right back where you want, incorporating the new data. So if you want to do an online estimation, update stuff as new information becomes available. For example, in maximum likelihood, this would work very, very well. Okay, let's talk about solving KKT systems. This is very important because, well, I guess a lot of people don't seem to know it. I guess people who do these things know it, but then they don't get around that much or something like that. So to solve a KKT system, and that's for infeasible start Newton method or for standard Newton method with equality constraints, you have to solve a system of equations that looks like that. And that's called a KKT system, just because this thing comes up. By the way, it doesn't only come up in optimization. It comes up in mechanics. It comes up in tons of places. I've seen it. I guess I opened the first book of some book on simulating flows in porous media, and like on page 2, I saw this. So, I mean, they didn't call it A, and they didn't call it H, but it was basically the system. So the system of equations is probably worth knowing something about. So here's how you could solve it. I mean, the first thing is just treat the whole thing as dense. It's m plus n, right? Because that's n by n, and that's m high. And so in the worst case, you just commit to this and solve that, just using absolutely standard methods, which is to say, in other words, this is the h. Let's see if I can get it right. H, a prime, a, and then zeros of the right size, backslash v w. So that's your well, that was all wrong. Minus, and this should be g h. Okay. So this is your that's your just default basic method. This will simply treat this matrix as dense. It is true there's a block of things here that are zeros, and this is fine. It'll do whatever pivoting it needs to do to make this stable, and it may even do the right thing. One thing it cannot possibly do is it can't do a Cholesky factorization on this. This matrix is symmetric, but it is for sure not positive definite because the zero's on the diagonal here. And in fact, your homework, which we, I forgot to announce that, we've backed off and said that you don't have to do, is it 10.1b, I think it is? Yeah, so some people have already done it. We heard from them last night. Anyway, were you one of them? No, okay, so, all right. So it's certainly not positive. You can't use a Cholesky factorization because this has negative eigenvalues. Okay, so one way to do this, probably the simplest is just an LDL I mean, the correct method, if you're just going to solve the equations, is LDL transpose factorization. That's a generic factorization for a matrix which is symmetric but not positive definite. If it was positive definite, of course you'd use a Cholesky factorization. And you use an LDL transpose. Now, in fact, there's a whole subfield now on KKT solvers, and you can go to Google and type KKT solver. You'll get maybe 30 papers on it, and codes if you want. So this comes up enough that it's studied carefully. But if you want these generic methods, you do something like an LDL transpose factorization. By the way, this might not be a bad idea if this is sparse like crazy here. So if your A is huge and sparse, if H is sparse, and what does H sparse mean in terms about F? I mean, actually, it's not at all uncommon that H is diagonal in these systems. In fact, I guess that's your homework. In your homework, H will be diagonal. Okay. So then this thing has just got tons of sparsity. It's just structure. It's just screaming at you. If you have ignoring, if that's a little block of zeros, you ignore that. That's maybe okay. But a giant diagonal matrix just sitting there, and if you ignore that structure, that's kind of irresponsible. That's over the line, I think. Anyway, LDL transpose factorization would probably work quite reliably here, and would take you up to some very, very, very large systems that just work. You can also do it by elimination, and elimination is interesting. It works. Well, you eliminate the first block, and you get this. So the first thing you have to solve is this equation. This is one of these you'll see is the Schur complement is going to come up somewhere. Well, I guess this is the Schur. One of these is the Schur. That's the Schur complement. This is 0 minus, it's 0 minus this times the inverse of that times that. So that is the Schur complement. Actually, it's the negative Schur complement because there's a minus sign there. Here's what's interesting if you do this method. This is interesting in cases where H is easily inverted. If H is dense, and there's 1,000 variables and 100 inequalities, this is actually not at all a good method to use. You might even just use LDL transpose here. Well, I don't know. This would be equivalent to it. However, if H is, for example, diagonal, meaning that F is separable, then H inverse is a non-issue. If H is banded. If H is sparse enough, H inverse is something very, very easily computed. Actually, I should say correctly. Although that's what people would say, they don't mean it. You don't actually compute H inverse, obviously. What you do is you'd have a Cholesky factor of H, sparse Cholesky factor, hopefully, and you would back substitute the columns of A transpose. Okay, but you know that, so I won't say that. So people would still say form this when you're not really. You do form this matrix. What you don't form is you don't form that for sure. Okay, I mean unless H is diagonal, then you would form it. But if H is banded, you would not because H inverse is full. Okay, so you'd form this. And the interesting thing is that when you solve the reduced system, you get a negative definite system of equations. I flipped the sign on it because if it's negative definite, it means you flip the sign. It's positive definite. And this is the Schur complement. Well, assuming H is invertible, then this can be solved by Cholesky. So in fact, if you solve this by elimination method, you will have 2 calls to a Cholesky factorizer. The first one is to H itself. By the way, that might not even be a real call if H is diagonal. Then there's no call because diagonal is trivial. But in other cases, there'd be a call that you'd do a Cholesky on H. You'd form this matrix. That's the Schur complement. And then you'd actually solve this by some kind of Cholesky factorization. So I guess people. That's another way. So people would call that maybe the elimination and Cholesky would call. But you're going to make you may be making up to 2 calls to Cholesky factorization. Okay. Now in some cases H is singular, but in this case you can do things like this. You can add any multiple of A transpose A with a Q in the middle like this. Solve this equation and it's the same. So sometimes there'd be something like A should be all positive and like one or some little block of zeros, and it doesn't matter. But this can be done, that's all subsumed in solving this set of equations intelligently. So let's look at an example. It happens to be exactly the example that you're going to solve on your homework. Of course, that does imply that all of the source code for this you can find, because it's all posted. So I think every example in the book, all the source code is there for it. So if you want to see how we did it, you can. But we'd encourage you to try to do it yourself. But there's no reason to bang your head on a wall. So you're welcome at some point to look at ours. See if you like ours. Actually, you can find it anywhere. There's tons of places. OK, so let's look at it. So here you want to minimize minus the sum log xi. That's the so-called log barrier for x strictly positive, subject to ax equals b. We have a point x which satisfies ax equals b and x is positive. So we start with that if we do the whatever you call it, the standard Newton method. Now the dual problem for this is maximize minus b transpose nu plus some log a transpose nu plus n. So the n, of course, doesn't matter, but if you want the optimal value of this to equal the optimal value of that, then it matters. And in this case, the function in the Lagrangian, which involves it's ax plus, it's actually the sum of the logs plus nu transpose ax minus b. That Lagrangian is strictly convex in the xi, and that means you can, if you solve the dual, you can recover the primal optimum by minimizing the Lagrangian. Okay, so that's how that works here. So in this case, you can solve either one. You can reconstruct the solution. In fact, basically, if you solve the primal problem, you're going to solve the dual whether you like it or not, and vice versa. By the way, this is quite interesting, this topic, because, in fact, I even, for a long time, was sort of ignorant about this. A lot of times, people get all excited or bent out of shape over, like, the dual or something like that, because what will happen is this. They'll have a problem, I don't know. They'll have this problem here. Xi will have size, I don't know, X will have this size 10,000, and there'll be 100 equality constraints. And they'll say, wow, you could solve a problem with 10,000 variables. Or, look at that. You could solve this dual, and it only has 100 variables. Boy, I'd really rather solve a problem with 100 variables than 10,000. Okay? And that would be true if you don't know what you're doing. Speaking with respect to numerical linear algebra, it's absolutely true, for sure. In that case, if everything costs you n cubed, where n is the size of the system, there's no doubt you want to be solving 100 variable systems, not 10,000. Okay. What's actually going to work out here is it turns out it's actually absolutely identical, solving the primal, dual, all of these methods. The order is the same. It's only the same if you know what you're doing with respect to linear algebra. If you don't exploit sparsity, then you will find gross differences. By the way, if you make that mistake, and I've been there myself, so I speak as a reformed someone who once didn't know these subtleties. You can make stunning claims. You can say things like, "Well, I found the best way to solve this problem. It's amazing. You solve the dual instead, isn't it? Genius, isn't it?" Right? Now, by the way, there are cases where there might be some convenience to solving the dual, like you might end up with a distributed algorithm. But in terms of numerical linear algebra, it's just wrong. Solving the dual is the same as the primal if you know what you're doing. Okay, so these are the two problems. You'll solve this one. Well, you can solve whichever one you like. So here's some examples. The first is, and they have different initialization requirements, and these are quite interesting. And in fact, that is actually the only thing that should drive the choice of method, assuming you're going to do everything right. Initialization. So if you're going to do Newton method with equality constraints, that requires a positive x that satisfies ax equals b. Now, by the way, this is checking whether a linear program has a standard form linear program has a strictly feasible starting point. That can be hard. There's no reason to believe that's simple. If I just walk up to you and say, here's A, here's B, please find me a positive x that satisfies x equals b. That's as hard as a linear program, basically. Because I'm basically saying, check feasibility, the standard form linear program. So, on the other hand, it depends on what the problem is, right? If this is some resource allocation problem or something like that, it might be completely easy to say what to get a point like that. For example, if it's a portfolio allocation problem, I mean, it might be that here's an initial x0. If you have 10 assets, $1 to invest, put 10 cents on every asset. Might be a stupid portfolio allocation, but for one thing is certain, it's feasible. I'm just saying that, it depends on the situation. There can easily be, in some cases it's easy to get such an x0, and others it's not. Okay, so if you do this, here's what happens. This is a plot of f minus p star, so it's in fact this is the suboptimality. And the scale, you can see, is extremely broad. It goes from like, 300 down to 10 to the minus 10. And this is the thing you want to look for. If you don't see this, if you don't see these plots rolling over, then you haven't achieved quadratic convergence. So, by the way, sometimes, well, you can get things where it's much more subtle. I mean, these is just sort of very much in your face here. These are the right numbers, 10, 15, 20 steps. These are, big problems. And let me say a little bit about this. Sometimes it's much more subtle and it just curves a little bit. And if you're banging your head, that's enough. But if it kind of looks straight, then you really can hardly claim that you've reached, that you're achieving quadratic convergence. It probably means something's wrong. So, by the way, out here, what would the step length be? What would you expect the step length to be out here? 1, right? So real quadratic phase is characterized by unit steps and quadratic convergence. That would be out here. What would you expect the step lengths to be here? What? Well, they certainly could be less than 1, but they could also be 1. The answer is you don't know, but you wouldn't be surprised if you started seeing if there were lots of steps out here where you were less than 1. Okay? All right. So this is it. This is just four different maybe starting points here, is the 4 different trajectories. Okay. That's the first. This is the method you'll implement. Now you can also solve the dual here, but totally different size. The dual has got far fewer variables, right? Well, not far fewer. It's got m, and I'm assuming sort of here. Well, m has to be less than n, but it's got fewer variables, so it's got m variables. Okay. Oh, by the way, here's an extreme case. Well, let's go all the way to the caricature. Ready? Here's the extreme case. Find the analytic center with 1 inequality. 1 equality. So that's just A transpose X equals B, X positive. Okay? Here, I think there's a couple things you could say. Let's see how to solve it. The dual has how many variables? 1. How do you solve a one-dimensional convex optimization problem? How? Yeah, you could do a line. I mean, you can do bisection if you like. I mean, you could do anything you like at that point. Okay. And you'd think, oh, wait a minute. Wait. I've got a million variable problem with 1. So this might be an image. That's an equality constraint. By the way, it's a stupid problem. But anyway, you have an image with an equality constraint, and you want to calculate the analytic center, which would be and you could wrap some big story around it, like it's the maximum entropy image or something with this, just some, who knows, satisfying 1 equality constraint. Now you can do it by bisection here. Your dual has 1 variable, and you'd say, that's ridiculous. How could the primal that has a million variables, how could that be as easy to solve as the dual? It seems suspicious, doesn't it? So we'll get to it. Actually, it's pretty straightforward how that works out. The KKT system would then look like this. The Newton system would look like this, where that's diagonal, right? So it would look exactly like that. Indeed, it is 1 million by 1 million. I would not recommend storing it as a full matrix, just so you know. But if you stored this as exactly in this form, you should look at that and say, well, that might be a million equations with a million variables. How fast can you solve this, roughly? It's in n steps, okay? So actually, what are we talking about for a million? Milliseconds at most, okay? So anyway, so these are very important to know, these things, and to recognize them. I guess there's a lot of people who know you could solve that fast, although a lot of them haven't totally internalized it. What they haven't also done is they haven't propagated this knowledge into the rest of their life. So they're doing signal processing or statistics or whatever, and they haven't put it all together. They don't know what a statistics problem looks like that happens to be one that you can solve unbelievably efficiently like that. So, okay. All right, let's look over here. So this is the Newton applied to the dual. By the way, this is interesting, totally different initialization requirement. What you need to, here is you need to find a vector nu for which A transpose nu is a positive vector, because that's how you need to initialize this problem. This is completely unconstrained. Okay? And you're going to, so you need this. Totally different problem, initialization requirement. And this one has, 9 steps to converge. And again, you see this thing roll over. That's the good, that gives you that good Newton feeling. Okay, if you apply infeasible start Newton method to this problem, so I initialize it with, let's say x equals just all 1s. Okay, I just plug in all 1s. You're very happily in the domain here, but you don't satisfy ax equals b. And that takes, here are the four things here. What I haven't marked here is where primal feasibility is achieved. And so let's make some guesses. If I told you that primal feasibility was first achieved on this run here, what would you tell me? You believe that? When do you think it was achieved? I'll go back. You say when. Probably somewhere around here. Why would I say that? Well, I say it for this reason. If you put everything together, it works like this. If you take a step of 1, you will be primal feasible at the next step, and you will remain so. So you'll satisfy ax equals b. If you take a step of 1. We associate quadratic convergence with 2 phenomena. Number 1, quadratic convergence. That's this rolling over of this, that's this thing. That's the famous doubling the number of digits of accuracy at each step. That's this rollover. And we associate it with step of 1. So when you sort of start seeing this rollover, you have taken a step. You're probably taking steps of 1. In fact, almost certainly. That means you're feasible. So although I haven't marked it here, primal feasibility is probably achieved somewhere in here. It could be up here. I don't know. And same for this one. Primal feasibility maybe is achieved like here, I'm guessing. Maybe here. I don't really know. Maybe I'll go back and replot these with filled in open circles to indicate when primal feasibility is achieved. By the way, note that the number of steps is not, it's changing within a factor of 2. It's 9 steps versus 15 and 20, and there's one that's 21 steps. This is not worth getting all bent out of shape about. It's not worth anything. Okay. Now let's look at what's required in to solve for the step in each method. If you use the first method, this is the one. By the way, this is your homework problem. You have to solve this system here. Now, in this case, you end up solving A times a diagonal matrix times A transpose W equals B. That's the only step here that costs you anything. That's diagonal here. So you have to form this matrix and then solve this system. Okay? Now, in the second case, for the dual problem is completely unconstrained. Here it is. It's this. You just simply maximize this function. You calculate the gradient and the Hessian. You calculate the Hessian inverse times the gradient. End of story. Now, the Hessian of this, I think you know actually from the last homework, the right way to do it is really under no circumstances should you sit down and start calculating partial squared this, partial nu I, partial nu j. That works in theory. It's a huge pain. Instead, use a composition rule. The Hessian of this is the Hessian of a function which is a sum of logs. That's going to be diagonal Hessian. Then you multiply on the left and right by A and A transpose, and I forget which one goes where. But one of them goes on one side and the other on the other. That's the chain rule for the Hessian. Well, here's the answer. You do this. Now, so to compute Newton method for the dual, you get this. Now, what's kind of cool about this is it's actually quite interesting. To solve this primal one, this primal Newton and Newton. Let's see. I have to be very careful. This is the. You're applying Newton to the dual here. This is applying Newton to the primal. You don't solve the exact same set of equations, but the structure of the equations is identical. They all have they both have the form. They're different matrices, but they have the form A diagonal A transpose. Down here, A diagonal A transpose. Different diagonal. Everybody see this? So you solve the same thing in this extreme case that I talked about. A is a row vector that's 1 by 1 million, then when you solve this system, this is basically a number, but then it's here too. So it's identical. Okay. If you use block elimination to solve the KKT system here, that's to solve the infeasible start Newton method. It's the same story. You solve the same thing here, but the right-hand side is different, but the matrix is the same, and that's what determines how fast it is. So in each case, you have to solve A d A transpose W equals H with a diagonal, positive diagonal. So that's actually all that's going to happen in all of these cases. So if A is sparse, then it basically says the computational complexity of the three methods is absolutely identical per Newton step. If you add to that the fact that the Newton method is going to take somewhere between 5 and 20 steps or something like that, and you call that just a constant, then it means that all the methods are just the same. There's no, and in particular, it means there's no dramatic improvement you're going to make here, just none. So, okay, everybody get all this? So, by the way, if you don't know how to solve these linear equations, everything's different, right? That the three methods are dramatically different, but all you're doing is displaying your ignorance of how to solve linear equations.
So, this problem, because you're solving the dual problem, you don't have any constraint. Is it a benefit because it's easier to find the starting point?
No, not at all. I mean, you could use the infeasible start Newton method. If you don't have a feasible point.
Because if you have a feasible start point, then you have more number of Newton iterations.
No, I know what you're saying. I mean, I also had this urge, and in the past did not know these things. Yeah, you want to say one of these is, you would like to say one of these methods is better, right? Well, we've just discussed the computational complexity issue. It's if you know what you're doing. That's a big if. It's identical. So the cost per Newton step is the same in all cases. Not because you're solving the same set of equations, because you're not solving the same set of equations. What you're doing is you're solving a set of equations with exactly the same structure. That's why it's comparable. Okay. Then you could ask, does one take more steps than another? Well, I don't know. No, not really. I mean, within a factor of 2, they're all the same. Okay, so if you here in this example, the dual method looks, solving Newton to the dual looks better. I can make another example where it's worse. Okay, okay. So everything comes down to initialization, and there I can think of situations, practical situations, where all three methods are the best one. So, or there's just no difference between them. So, I hate to say it, but I think they all have, at the moment, they all have equal status. The main thing is the initialization. As to which one is better or whatever depends on the situation. If you have an obvious dual feasible point, fine. If there's an obvious primal feasible starting point, fine. If you have a guess of a point which is nearly feasible but not quite, you might want to use infeasible start Newton method, and so on. So, okay. So now we'll look at some other examples. They're fun, and they all have the same theme, which is you look at a Newton method, and then we'll talk about forming it, but what you're really doing is you're looking for structure to solve here. So let's look at network flow optimization. So network flow optimization is this is a single commodity flow. It's a beautiful problem. You should all know about it. So you have a network, a directed graph like this. It doesn't really matter. I mean, and you have flow on the edges. And a flow, these arrows actually only tell you the orientation of the flow. So it's like in circuit analysis. You make an arrow here, and that tells you that if current flows that way, you will regard it as positive. If current flows this way, you will regard it as negative. So that's the. Now, it could be that, in fact, things can only flow this way. There are many cases where that's the case. But generally, when I mark these, this is what you have. So then you have things like this could be a single commodity network or something, commodity flow. So then you have external inputs to the network. You have one very important requirement. The requirement is that in circuit theory you call this KCL, which is Kirchhoff current law, and it basically says that at each point flow is conserved. The sum of the flows at any node is 0. Okay? So that's what it says. And sum of the flows means if things are, it's this, some people would say the sum of the inflow is equal to the sum of the outflow. Another way, this is the same, and you get this in lots of things. You get it in physics, you get it all over the place in anything. It's mass conservation, for example, or it's just a conservation. It just basically says the flow is conserved at nodes. And if it's a differential equation, I guess you'd say it's divergence free or something like it, whatever it is there. Okay, so and you can think of this as any way you like. These could be flows of packets on a network, and the fact that it's conserved says the buffer is bounded, or there's either no buffer or the buffer is bounded and it's not growing or something like that, and it's in steady state. It could be actual current. These could be amperes, and it says you're in steady state or something like that. Okay. Okay. So this is that's flow conservation. You have some external sources and sinks. So it's generally, if you're pumping stuff in, you call it a source. If you're pulling stuff off, it's called a sink. Actually, I'm just drawing these as if all the variables were positive here, for example. But of course, this could be a source if this flow is negative. Now, in this case, you have to have the sum of the sources 0. That's very easy to work out. Otherwise, it doesn't make any sense. So that's a network. Now, there'll be lots if you fix the external flows. So if this is a distribution network or a current network or something like that, we'll make it a product distribution network. If this one is pumping in something, this is pumping in something, this is pumping in something, then what you're pulling off here at the sink has to be equal to the sum of these. But there are lots of flows in here that satisfy the flow conservation equations. So you can actually route the flow any way you like. Routing the flow basically means what comes in here, some you shift there, some you shift there, some you shift there, and so on. Okay? So that's the picture. And in fact, this is just written as AX equals B. B is the source vector here at each node, and A is the incidence matrix. So that's the matrix, you've seen this, or should have seen it, that looks like this, where you have nodes and edges like that. And you have a +1 or -1 to indicate where where that edge goes, the from and to node. So that's just AX equals B. Now, among all the possible feasible flows, by the way, there's all sorts of interesting things you can say. The null space of A, for example, is called a circulation. Because if I add something to null space here, so a circulation might be something like that. Notice that it does not affect the external flow. It adds to this flow, adds to this one, subtracts from this one, and subtracts from that one. It subtracts because my circulation is going against these things. So that's an element of the null space. You might ask, why on earth would you have anything to do with one of these? Well, we'll see why. What you want to do is you have a cost now on every edge. And you want to satisfy the flow equations, and you want to minimize the total cost. So, by the way, let me just quickly ask something right here. There's something that should pop out if you're fully trained and all the neural pathways are hooked up correctly, created. You should be able to look at that, and without even thinking, 50 milliseconds later, a picture of the KKT structure should show up in your head. And what is it? Okay, when you see that sum of scalar functions, what is the Hessian? Thank you. So you should just look at that and see in your head this without anybody saying anything else. That's what you should see when you see this. Okay? So, it should be just an autonomous response. Okay. All right. Anyway, we'll go through this. This is the reduced incidence matrix. And let's look at the KKT system for this. The KKT system looks like that. So H is diagonal. That's the important part, is that, of course, you should always see this when you see an equality constrained minimization problem. But in this case, that's very important. That's diagonal. You can solve this via elimination. You have A, H inverse, A transpose, W equals this thing. Now, of course, when you actually go to write the code, you have to get all the right-hand sides correct and all that stuff, or it's not going to work at all. But in your first pass over a problem, you want to think about the structure. And so basically in this problem, the inverse shouldn't bother you at all because that's a diagonal matrix. So although normally an inverse would set up a red flag, which is you need to look at that. Is that hard, easy to do, and so on. In this case, it just goes away. It just, yeah, of course you have to actually carry it out correctly in your code, but it's a non-issue. All right. So basically what it says is if you want to solve a network flow problem, each step of Newton's method is going to require you to solve a system of the form A diagonal A transpose. By the way, that's a theme. You might have noticed it. You will hear about A diagonal A transpose actually just everywhere. That's, you might ask, like, what do you do when, if you wanted to ask, what does SPICE do? You know what SPICE is, right? Circuit Simulator Program. You might ask, what does SPICE do? Would you like to know what it does if you profile it? It's solving systems that look like A, D, A transpose. That's the only thing it does. Everything, and I'm talking about for all calculations it does. Everything. DC, as if you, actually, how many people know what I'm talking about anyway, or know about SPICE? Okay, so you get the same, if you do a thermal simulation, right, you're solving A, D, A transpose for a finite element method. If you solve a Poisson equation, what do you think you're doing? You're solving a system of the form ADA transpose. So it's just, so there's no reason, you might as well accept the fact that it's everywhere. And you have seen it, you will see it, you will use it. You'll use it many times when you don't even know you're using it. Okay, so I'll have to think about where you're using it in machine learning or something like that. But I'm sure you are somewhere. I just don't know where exactly right now, but I'll think of it and tell you. I'm sure there's somewhere where you do this, some Bayes network calculation or something. But anyway. Okay, so you have to solve that. By the way, the sparsity pattern of A diagonal A transpose is extremely easy to work out when A is a graph incidence matrix. It's very, very easy. It turns out that A diagonal A transpose Ij is not 0 if and only if, that's a nodes by nodes matrix that you're solving. And that's true if and only, it's non-zero if and only if I and J are connected by an arc. So that even tells you now about the sparsity pattern you're going to see. In fact, I can ask you some questions now, and we'll see how well you've I just want you to guess or whatever, and you tell me. Suppose I have a network. I want to do network flow optimization. My network, the fan out, or the degree of each node in the network is like small, like 3 or 5. But it's got 10,000 nodes. Do you think we can do optimal flow fast on it? Yeah, probably. Because if you form A transpose A, it basically says, it tells you something about the number of non-zeros per row in this thing, right? And the answer is, each row's got if each node is only connected to like 3 others, that's the number of non-zeros per row or column. Okay? So that's how fast can you do it? I don't know. It depends on the gods of heuristic sparsity ordering methods and whether they're smiling on you that day or not. But the point is, it's likely you can solve that problem very, very fast. Now let me ask you this. Let's have a node, a single node is connected to a huge number of others. What does that do? In sparsity pattern in A H inverse A transpose. Everybody see what I'm saying? So, in fact, let me draw my network. I have a network here, which is kind of sparse. Everybody is connected to just a few others. I don't know. It doesn't really matter. Okay, but I've got some supernode here, and it's actually connected to a whole bunch of them. What does it do?
Permute it to the bottom. Want to just preserve your arrow structure?
Okay, yeah. If you permute it. Okay, very good. So your proposal is that this should be ordered last. Okay, and what is the sparsity pattern on A H inverse A transpose if you order this last? In this case, what's the sparsity pattern on this thing? It's arrow. Yeah, well, no, it's like sparse arrow or something like that. You get a sprinkling of entries from these guys, but from this one guy attached to all of them, that is going to give you a dense row and column in this matrix. Okay? Now, by the way, you could order it to be the end, but in fact, any decent heuristic for ordering is going to put that guy at the end anyway. So, but you'll know it's going to work. In fact, you'll know that if you had a network with 10,000 nodes, and the degree of most edges is 3, but 100 of them are connected to giant piles of nodes. We'll call those super nodes or whatever, it doesn't matter, whatever you want to call them, right? Because you're maybe optimizing the flow on a peer-to-peer network or something like that. You would know what the structure is. The structure will be dense with 100 much denser rows and columns. And you'll know actually that that can be solved very, very well. Maybe you'll know, but anyway. Okay, so I didn't expect everyone to follow all of this, but this is the kind of thinking you want, I think you want to do for this stuff. You want to just be on your toes connecting sparsity and structure to the actual problem at hand. And that the problem at hand, it'll be things like, bottlenecks, bottlenecks, super nodes. That's for this one. But for every problem, there's going to be something like that. Okay, we'll look at one more. It's an even more advanced one, but it comes up in a lot of things. You want to calculate the analytic center of a matrix inequality. Let me just first motivate it a little bit. This comes up all the time, but I can tell you what this is. This is the following problem. I have a covariance matrix, and I tell you some things about, well, let's see. I have a random variable z, let's say, and let's make it Gaussian or something like that. Let's just say it's Gaussian. Okay, so it's n0 sigma. Actually, I'm going to call its covariance matrix X. Okay, and here's what I'm going to tell you. I'm going to tell you some variances of linear functionals of z. So I will tell you, for example, I've got a vector c, ci, and ci transpose z, I'll tell you the variance of that. Now this is nothing but ci transpose x ci. Everyone agree with that? It's nothing but that. Therefore, that's the same as the trace of x ci transpose. The linear, the variance of this linear combination is a linear functional of X, the covariance matrix. Everybody agree? Okay. And now, so I'll give you an example. I have a random variable, and I say, well, the first component has variance 12, the second has variance 3, the fourth has this variance, the fifth has that. Oh, and by the way, the following, this linear combination of them has this variance. You can even do things like give the off-diagonal elements. I can say actually, element 3 and 5 are correlated 37%. Elements 6 and 12 are correlated minus 19%. So I just give you a bunch of partial information about a covariance matrix. And then I say, please compute for me the maximum entropy distribution that satisfies Gaussian, that satisfies those known constraints on the distribution. Everybody understand that? Well, that would be this problem. Maximize the determinant subject to some equality constraints. Okay. I mention this just to say this problem comes up. Okay, this comes up. Okay, so now let's talk about, let's solve this problem. Well, first of all, you look at it naively, you would say how many variables are there? Well, let's see. X is a matrix variable. It's square. It's n by n. And so therefore, the number of entries it has is this in it. Okay? Now, if there's p of these equality constraints, it basically says that if I form the KKT conditions or whatever, I'm going to have a matrix that's this big. Okay? So, and therefore, our baseline cost is that. Okay. Now, that is grows like n cubed, n to the sixth. I'm sorry, that's n to the sixth. Everyone agree? Because this is n squared inside a cube. This would start getting tough. You can't do a matrix bigger than 100 by 100 with this scheme. Not to mention, by the way, this scheme would be an enormous pain in the ass to actually write up, because here you'd have to find some way to encode, this thing, the vec operation there. Okay, everybody see what I'm saying? I could assign this problem. You could write a Newton method on it just like that. Theoretically, it'd be a pain in the ass, so we wouldn't do it. But you could. This is just like no problem. However, the complexity is going to be n to the sixth, which is not a great complexity. Okay, so let's actually see how you do this the intelligent way. It's exploiting all the structure in here. By the way, the structure this time is not going to be sparsity. So this is just an example. I mean, I wouldn't expect you to know this. A lot of people don't know it. Actually, to this date, don't know it. But we'll go through it. We'll do a little bit of it just to give you the flavor of it. The Newton step is solving a set of, well, look, the Newton step solves a set of basically n squared over 2 plus p equations in n squared over 2 plus p unknowns. The unknowns are delta capital X Newton and the dual variables nu, which is of which there are p of them. So that's what you end up, you have to solve a set of equations like that. It's a dense set of equations, by the way, completely dense in general, right? So there's no sparsity trick is going to help here. Those equations, however, look like this. They look like that. So that's a matrix equation here. So it's x inverse delta x, x inverse. This is, in fact, something like the Hessian, or it's complicated, but it looks like that. And there's a very simple way to derive this, actually. What you do is you just write out the optimality conditions, which is this here. Then you linearize this at the current x and the current nu, and write out that equation. If you do that, you'll get this. You'd get the same thing if you looked up and figured out what the Hessian of log det is, and you'd, I don't know, get a big headache and stuff like that. But then ultimately, you'd find out the Newton step can be expressed as a set of matrix equations that looks like that. So that's how, and you have to solve for this and that. Now this doesn't look good. However, there's a block in this system that we can solve fast, and I'll show you what it is. If I fix W, can you now solve fast for delta x here if I fix this part? If I fix this part, then I'm just solving x inverse delta x, x inverse is equal to a fixed matrix. How do you get delta x? That's a set of n plus 1 over 2 equations in n plus 1 over 2 unknowns. If you just go to your generic backslash solver, whatever, that's order n to the 6th. However, in that case, it's very easy. You simply take this thing minus that, and you multiply on the left by x, on the right by x. Okay? All of those operations, matrix multiplication, those are order n cubed. So if you know what you're doing, you can get, if the w's were fixed, you could get delta x here in n cubed operations. N cubed is a whole lot more favorable than n to the 6th, just for the record. Okay? So that tells you that although there's a dense block in this system, it's one that is easily solved by special structure. By the way, if you're curious what the matrix structure is, it's called Kronecker. It's a Kronecker product structure or tensor product structure, or something like that. So that's why this is fast to solve. So you solve it by block elimination. You eliminate delta x to get this. You substitute this into the second equation, and you get this. And now you look at this, and you realize that's a set. This, you can write this. This here is something that looks like this. It's here, G W equals B. The entries of G are this thing. If you work out what the computational complexity is, you have to calculate every row, every entry of G, and then solve this. That's cheap. That's P cubed. But the computational complexity comes out to be this. That's going to be one of the leading terms is going to be this. It depends on the order of n and p, but they all look like this. The cool part is it's order n cubed. I mean, so whatever the complexity is, it for sure beats the generic one, because this thing actually starts out with an n cubed term. It's n to the 6th. It's also got a p cubed term. We've got a p cubed here, but our complexity clearly is way, way, way better. So I didn't expect people to follow all that, but it's just to show you that once you learn these ideas of looking for structure and block elimination and things like that, it will come up in lots of places, and it will be surprising. By the way, I didn't know that there's been periods when I didn't know this. I've solved problems without knowing this, and that was a mistake. In other words, I'm saying I made a mistake. We did it for years and so on before we knew all these things, or knew how to articulate these things, because sometimes you see these things and they just look like some secret trick, and you think, why would anyone think to do that? It's just some one-off little trick. Anyway, so that's it's not. It's just block elimination with some sophisticated methods for solving structured equations. Okay, so that finishes our discussion of Newton method, and we're on to our last topic, which is interior point methods. And let me explain first the big picture, how that's going to go. It's going to go like this. You're going to have a problem with inequality constraints, let's forget the equality constraints because they don't matter. So we're going to have a problem with inequality constraints here. We're going to solve it, that's our next step, by reducing it to solving a sequence. We'll solve a sequence of smooth, unconstrained problems. By the way, I'm going to put something above it. Like I'm going to put a little note above it. I'll fill that note in later. But we're going to have an inequality constrained problem. We're going to solve it by solving a sequence of smooth unconstrained problems. How do we solve smooth unconstrained problems? Newton's method. What does that mean? We actually are solving a sequence of, this arrow means solve this one by solving a sequence, and I mean a small number, like 10 or 15 or something like that. I don't mean some huge long limit. I mean solve a sequence of these. So you solve 5, 10 smooth ones. The smooth ones we do by Newton's method. Newton's method is the same as solving a set of quadratic unconstrained problems. Now, to solve a quadratic unconstrained equation, that's the same as, these are linear equations. Oops. There you go. These are linear equations. Okay? So, and we know, there's lots to say about this. By the way, this note up here would be, you might start with a non-differentiable constrained problem, right? Like you want to minimize the L1 norm subject to AX equals B. Let's say you wanted to do that, for example. Okay? The objective is not differentiable. You can't solve it. I mean, you can't use Newton's method on or anything like that. It doesn't fit this category. So there we do a transformation. So this one is a transformation. To minimize the one norm, you do a transformation that goes like this. You'd minimize the sum of the TI subject to absolute value xi is less than ti, which you'd write as, I guess, xi less than ti minus xi less than ti, right? Everybody knows that. And so you take a problem which is non-differentiable, equality constrained, and you convert it, you add new equality constraints. Now you've added all these new variables and constraints, and you might start getting all nervous and weird about it. But if you just remember that, I guess, the size of the problem is not what matters. What matters is the structure. Then you'll be okay. And actually, you'll even have a sense when you're doing this that when you're adding these little inequalities, they're very local, and so they're going to contribute to sparsity in very, very favorable ways. Okay. So, but I'll assume you start here. So, smooth unconstrained, you do that by Newton's method. In each step of Newton's method, you are actually solving a quadratic unconstrained problems, otherwise known as solving a set of linear equations. So this is how this is the hierarchy. The first thing is just to know how it's done. The second is to understand that at the end of the day, when you profile a code running it, it's only solving linear equations. That's why you need to know how to solve linear equations. And the more you need about how to solve them and about exploiting structure and things like that, better off you are. Because the equations you get down here are going to inherit structure all the way up from this one at the top. I mean, L1 optimization being a perfect example. Okay? So a lot of people don't know this, but this is, but you will. So we're now going to talk about this step. How do you solve an inequality constrained problem by solving a sequence of smooth unconstrained problems? Or equality constrained. I mean, they're basically the same. That's what we're going to do. So we're going to solve this problem. All the f's are twice differentiable. By the way, to get to this point, you may have to do, as in an L1 problem, you may have to do a transformation to get to this point. So if your f's are not differentiable, you might have to do a transformation. But I'm assuming you've done that, and now we have the inequality constrained, smooth inequality constrained minimization problem. Okay. Well, we'll start by assuming that we have the problem is strictly feasible. And so I can find a point that satisfies the equality constraints. All the FIs are negative. So that's Slater condition. And that means that if I write down the primal and dual, if I write down the KKT conditions, they're necessary and sufficient conditions for optimality. So what would be examples of problems like that? Well, obviously, LP, QP, QCQP, GP, these are all obvious. GP in convex form, of course. Examples that are not quite like this, you have to be careful with. Things like SDPs and SOCPs, you can actually formulate them this way, but it's quite tricky. And it's better to do this by cone programming, which we'll get to soon. Okay, another example would be entropy maximization. So entropy maximization says this. Minimize negative entropy, subject to some inequality constraints, right? So if X really is a distribution here on some finite set, then one of the constraints, of course, is that X is, it's that they sum to 1. So that's one row in A is all 1s. And then the other rows in A are, this is just the expected value of any function of a random variable. So I can have a random variable on 10,000 points, and I could say, I could give you some moments, I could give you some probabilities that are fixed. I can give you I could give you intervals. I could say the probability that X is in this set is between 0.2 and 0.3. Those would translate to this. I could tell you all sorts of things about the skewness and the kurtosis and whatever else I like. Those will all translate to linear equality and inequality constraints. And then I might say, please compute for me the maximum entropy distribution that satisfies those conditions, those prior conditions on the probability. And that would be this problem. This is a good example of a problem like that, because here the inequality constraints are affine here. So they're obviously smooth. And the objective is also smooth. Okay. All right. So we'll get to this idea of the log barrier. And it's actually an embarrassingly simple idea. It works like this. I want to convert that problem to one I can handle. What can I handle? Well, we just finished looking at equality constrained smooth minimization. So what I'm going to do is take this irritation function associated with a hard constraint, and it looks like this. It's 0, and then it goes up to plus infinity. Okay? It's the indicator function of the feasible of actually R minus. Okay? And what I'm going to do is I'm just going to replace that with a function that goes to infinity as you go here, and then but is otherwise smooth. And what we'll do, I mean, a typical example would be like a log function, right? So this is called a barrier function, something like this. And basically what it says that instead of being totally cool until you hit 0, this is for a constraint, and then basically going totally insane, because that's the semantics of the original problem. It basically says that it depends on which one you want to pick here. But the point is, you start getting nervous when a constraint starts getting close to infeasible. That's what these, then how close do you get before you start going nuts? Well, that depends on how good your approximation is. And over here, you might feel more and more comfortable the more margin you have. I'm just anthropomorphizing this, but that's kind of the idea. So the idea is you get someone who, instead of someone who goes insane, is totally cool until a constraint is violated and then goes insane. You want something where the more margin you have, the cooler you are, moderately. And you start getting nervous when you start getting close to this. Of course, you still go insane if it's infeasible here, right? Okay, so that's called a barrier. The most common barrier is something like a way to write it out is this: is you have 1 over t. You have a parameter 1 over t times the sum of the log of the negative things. That is a smooth convex function. You know that. Sorry. There, with the minus sign. That's a smooth convex function. And the parameter t simply sets basically the scale of how nervous you are, depending on how close something is to getting feasible. If t is big, it basically says that your logarithmic barrier here is actually giving you a very good approximation of the true function here. It's very flat, near 0, then shoots up to plus infinity. If t is smaller, like 1, it means it might be this one out here, something like that. Okay, now that is a smooth problem. This thing. This is a smooth problem. We can solve that by Newton's method. Okay. Now, so we can solve this, and now you can think of all sorts of things. You could set t. You'd set t high enough. I mean, so there's a lot of things to do. I mean, the one thing you'd want to do is prove, for example, that as t gets bigger, the solution of this actually approaches the solution of the original problem. I mean, that's really what you want to do, right? I guess this is the original problem. Here, I minus is the one that goes like 0 and then plus infinity. So that's the original problem. You want to show that this approximates that, and it kind of makes sense that it would. The other thing is there's obviously something fishy here. If someone proposes to solve this by this, it should raise up all sorts of like red flags for you. Let me tell you how. Suppose someone says, look, I can't solve, it's kind of like this, and this actually happens. There's like grown people who say stuff like this. Works like this. Here's an L1 function, and they go, no, you can't solve that. And you go, why? And you go, it's non-differentiable, look. Now, let's leave alone the fact that you solve it precisely. What's interesting about L1 is precisely that point. It's that point there that makes, when you solve these things, lots of the entries 0. Okay, so let's leave that alone. So the standard method I call the sandpaper method. So the sandpaper method is this. I'm not going to say who does this or anything like that, but there's still grown people who go around and say this stuff. They go, well, everyone knows you can't solve that. So what you do is you get out your sandpaper and you go towards this tip and you sand it off. And you go like that. I mean, a typical one would be to say, look, I'll write it this way. There, then mine there. There's my function. Everybody cool on that? Okay. Now, this function on the right-hand side, analytic, totally smooth. Okay. However, the corner has been sanded down at the scale of 10 to the minus 5. Everybody agree? And they go, cool. That's just not twice differentiable. That's like 5 times differentiable. It's like 48 times differentiable. So I can use Newton on it. Now, do you go for that? If you apply Newton method to something that looks like the absolute value function with just a little bit of light sanding to get rid of that corner, what's going to happen? What is the Newton step, for example, like right there? What's a Newton step on a sanded absolute value function? Well, the gradient, what's the gradient? Like -1. What's the Hessian there? Don't, by the way, please don't calculate anything. Just use your eyeball. What's the Hessian? What is it? Is it 0? I don't think so. The Hessian of the absolute values function is 0. It's not, the Hessian of this is not 0, but you're very close. What is the Hessian? Almost 0. Thank you. It's almost 0. What's the Newton step at that point then? It's like some insane, huge, long step, right? Okay. But more than that, how well is Newton's method going to work on a sanded down absolute value function? Well, what do you have to ask yourself? You have to ask yourself this question. If you form a quadratic model of this function at a point, how good an approximator of the function is it? Well, what do you think? You think Newton's method is going to work on this? Well, of course, our theorists tell us, yes, it will. And indeed, it's a proof. Of course it will. But how well do you think it's going to work in practice, Newton's method on a sanded absolute value function? You get 2 guesses. And then we'll quit. The first is, like, super well. And the second is the opposite. It doesn't work, like, at all in practice. So which do you think it is? The second one, you're right. Okay. Why? Because it's obviously, and if then you say, well, how does it work in the theory? Right down here, the Hessian, this third derivative goes insane, right? Because the Hessian goes from, it goes through something where it goes super high, it's super low, it gets way high, then it gets low again. You have to get down to the scale of 10 to the minus 5 to actually see this curvature. So the point is, you're right, Newton's method on a sanded down thing isn't going to work at all. So I'm just saying that you shouldn't, when people do this business where they go, oh, it's non-differentiable, not a problem. Give me my sandpaper. You shouldn't, generally speaking, you shouldn't believe stuff like that. This one's going to work out, but this one does not. Yeah.
You were saying before that if we're solving a problem like that, though, we have to do something to make it differential before we even start this process.
Right.
So if that's not how you do it, then what would you do to make it?
No, that is what you would do. And that's the correct way to treat L1 constraints in most cases. You do exactly what I said. You add new variables, new constraints, and then use these types of methods. So, okay, we'll quit here.